So in this session, we will be discussing about the continued part of your last session, that is your previous session, session number 3, that is preparation of haloalkanes. Along with that, we will also be today studying about preparation of haloarenes. So today we will be having a continued talk about your preparation of haloalkanes as well as preparation of haloarenes. So in your previous session, the flow chart, we have seen that there are 3 methods of preparation of haloalkanes. The first one was from alcohols, the second one was from hydrocarbons, and the third one was from your halogen exchange reactions. So today we are going to discuss about the second method of preparation of haloalkanes from hydrocarbons as well as preparation of haloarenes even from these hydrocarbons. So the hydrocarbons leads to preparation of both haloalkanes and haloarenes. As a result, both together we will be discussing in this session. That is the preparation of haloalkanes and haloarenes through hydrocarbons. So first let us take the flow chart of this preparation. What is the flow chart? Followed by the complete explanation. So as we know, it is from hydrocarbon. First one, preparation of haloalkane from alkenes. How do you do it? By reacting with chlorine in presence of light or heat. Direct halogenation. Upon reacting your alkanes with chlorine in presence of light or heat, there is a direct halogenation reaction wherein the hydrogens of your alkanes is replaced by this halogen to give you your haloalkane. So that's your first method. The second method is from alkenes. Alkenes has 2 methods of preparation of your haloalkane. The first one would be by reaction with hydrogen halide following your Markovnikov's rule. So it's an addition reaction, addition of hydrogen halide. There is another method of preparation of haloalkanes from alkenes itself, that is by addition of dihalogen in presence of CCl4. Remember, both are from alkenes. The first one is from addition of hydrogen halide. The other one is from addition of your dihalogens. So these are the 3 methods of preparation of haloalkanes from alkanes and alkenes. So let us see one by one in detail how do you prepare these things and what are the details, more details about this reaction. So coming to your first method, it is from alkanes. It is direct halogenation. This you have studied in your first PUC itself. So if you see the reaction, if you take an example of methane reacts with chlorine gas in presence of light or heat, you get CH3Cl plus HCl. This is your chloromethane. The first thing you have to know about these reactions, that is direct halogenation, is these undergo reaction through free radical mechanism. That is, the intermediate involved in these reactions are your free radicals. I think you know this free radical mechanism of the above reaction in your first PUC in your hydrocarbons chapter. In detail we have studied about the 3 steps involved in this free radical mechanism: initiation, propagation and termination. So that's the same reaction we are taken here, wherein you prepare your haloalkane from your alkane by direct halogenation. The second thing you have to know about this reaction is, you know that the reaction doesn't stop at this point. That is, you don't get only chloromethane, instead you get a mixture of other compounds also. That is, all the 3 hydrogen atoms here present, they get substituted one by one through your halogens continuously, vigorously, wherein you cannot stop the reaction at this instance. That is, you cannot stop the reaction to prepare only chloromethane from this reaction. What are the other things do you get? The other products along with CH3Cl, you get CH2Cl2, CHCl3 and CCl4. You get this mixture of products. The isolation or separation of these products is very difficult to get one of the desired product. Say if this is the desired product, I have to separate these 3 molecules. If this is the desired product, I have to separate these 2 and even this one. So like this, the separation technique becomes very difficult in this method. As a result, this is not suitable for your laboratory method to prepare your haloalkanes. Since this is a mixture of product you get, the yield of one particular product is also very low. So say for example, this is about 20, 20, 20, 30. So the yield of one desired product is also very low. That is, one product is not produced, there are a lot of products produced, hence yield of one particular product will also be very low. So these are some of the informations that can be drawn from your direct halogenation reaction, wherein haloalkane can be produced by this method. The next method is from alkenes. So first method from alkenes is by addition of hydrogen halide. I have already told you wherever or whenever you see a double bond or a triple bond, the characteristic of that reaction molecule is your addition reactions. The first reaction which we have taken, it's a substitution reaction, while the second one, that is from alkenes, since it has a double bond, the characteristic reaction is addition reactions. Hence both these two reactions are, what type of reaction is? They are addition reactions. Let us see an example for that. So your alkene plus HX hydrogen halide to give rise to addition of hydrogen, addition of halogen. So across your double bond, the hydrogen and the halide adds up along the across the double bond to get this halo compound. So this is your haloalkane from your addition of hydrogen halide. So this is a symmetrical alkene, that is you can divide the molecule or cut the molecule into two equal halves. As a result, hydrogen halide doesn't have any rule to be followed. But if it is a unsymmetrical alkene, say for example, so if this is an unsymmetrical alkene, what do you mean by an unsymmetrical alkene? You cannot cut the molecule into two equal halves. So if I cut this molecule here there is a CH2, here there is a CH3. So for this molecule, if I add say HBr, it has to follow Markovnikov's rule. That is hydrogen bromide, addition of hydrogen bromide to an unsymmetrical alkene follows Markovnikov's rule. We have already discussed this in your first PUC. Also in your general organic chemistry sessions, what is this Markovnikov's rule? The code word you have to remember is NaCl. What is this NaCl? The negative part of the reagent adds to the carbon having least number of hydrogens. So in this reagent, which is the negative part, this is positive, this is negative. So the negative part of the reagent adds to this carbon-carbon double bond having least number of hydrogens. So if I take this instance as the carbon-carbon double bond, which is the carbon having least number of hydrogens. So this is carbon 1, say this is carbon 1, this is carbon 2. This has 2 hydrogens, this has only 1 hydrogen. Hence, this negative part of the reagent has to add to this carbon having least number of hydrogens. What is the product now? It is CH3, CH, Br, single bond, CH2, another hydrogen adds here. So this is the product. What is the name of the product? This is 2-bromopropane. So like this, if HBr is added to a symmetrical alkene, there is no such rule to be followed since both are symmetrical, both the carbons are symmetrical in nature. As a result, directly you can have the product. Either the hydrogen can be added to this carbon or this carbon, vice versa for your halogen. But if it is an unsymmetrical alkene, you should be very careful while adding the negative part of the reagent. That is because it follows Markovnikov's rule. Hence, you get your haloalkanes through addition of hydrogen halide. So this is your 2-bromopropane, the major product. Along with this, you get a minor product also, that is this is a minor product. This is your 1-bromopropane or simply it's your bromopropane. I think you also remember about anti-Markovnikov's rule, that is the same reagent in presence of H2O2, hydrogen peroxide, anti-Markovnikov's rule, the opposite happens, that is this becomes the major product and this becomes the minor product. That is, what is that anti-Markovnikov's rule? The negative part of the reagent adds to the carbon-carbon double bond having highest number of hydrogens. So that's the opposite one. This will be helpful for your CET. Even this method is one of the method for preparation of haloalkanes from the alkenes. That is, remember about CET anti-Markovnikov's rule. It is also called as peroxide effect and Karash effect also. So the last method of preparation of haloalkanes from alkenes, that is from hydrocarbon, is addition of your halogen, dihalogen in presence of your CCl4. Say for example, ethane plus bromine, that is your dihalogen in presence of CCl4. This adds across your carbon-carbon double bond to get like this, CH2, single bond, CH2. So remember, by addition reaction, the number of bonds, that is the bond order, goes on decreases. That is, if there is a triple bond, if you add a molecule across the triple bond, it becomes double bond. If you have a double bond, if you add a molecule across it, it becomes single bond upon addition of one molecule for one bond. So one molecule for each bond. So this becomes Br, this becomes Br. 1, 2 dibromoethane. And remember, what type of halides is this? It is your vicinal dihalides. I think you know what I mean by dihalides. Dihalides are nothing but the compounds with two halogen compounds. Vicinal means these two halogen atoms are present at the carbon atoms next to each other. So, neighboring carbon atoms bear halogens, two halogens each. As a result, they are called as vicinal dihalides. The important point I have to tell about this reaction is, this is a reaction which is used to detect an unsaturation in a given molecule, which is called as bromine water test. What do you do is, take a bromine water, that is bromine dissolved in carbon tetrachloride, add to an unsaturated molecule like your ethene. So, bromine water that we have taken here, it is brown in color. Upon addition to unsaturated molecule, it gives white color precipitate, that is bromine color has been discharged, which indicates that the molecule has unsaturation. So this reaction which we have studied, it is a test for unsaturation. Even this is studied in your practical also. You have this test to be studied in your practical also. It is one of the important tests to detect an unsaturation in a given molecule. The next thing is preparation of haloarene. That is by two methods. First one is by electrophilic substitution reaction. Take your benzene, aromatic hydrocarbon. Through electrophilic substitution reaction, you get your haloarene. That is halogen in presence of anhydrous FeCl3. That is nothing but your halogenation reaction. I think you have studied about 5 types of electrophilic substitution: sulfonation, nitration, halogenation, Friedel-Crafts alkylation and Friedel-Crafts acylation in your first PUC hydrocarbon chapter. The same thing here, you are taken your halogenation, one of the electrophilic substitution reaction. So this is one of the method. The second method is from diazonium salts. This is your benzene diazonium salt. Upon reaction with copper salt, so cuprous salt, which means that the oxidation number of this copper here, it is +1. You get this haloarene as your product, and this reaction is known as called as Sand-Meyer's reaction, a very important reaction in your board level as well as your CET. So the first method from benzene, and it is through electrophilic substitution reaction. So take your benzene, react it with chlorine in presence of anhydrous FeCl3. This is your Lewis acid. It helps in generation of electrophile. That is, this FeCl3 will combine with this chlorine and form the electrophile, respective electrophile for the electrophilic substitution reaction. So this helps in production of electrophile. Which is the electrophile here? It is chloronium ion. It is your electrophile. So FeCl3 will combine with this Cl2. The Cl-Cl bond has been weakened. As a result, it forms FeCl4 minus and Cl plus. Along with this, you get this FeCl4 minus. This electrophile attacks your benzene. As a result, what do you get? Your chlorobenzene is formed. In the same manner, you can also have a reaction of bromine in presence of anhydrous FeBr3 to get your bromobenzene as the product. While your fluorobenzene as well as your iodobenzene cannot be prepared by this method, that is through electrophilic substitution reactions, only these two can be prepared. Fluorobenzene cannot be produced by this method, that is electrophilic substitution reaction method. That is because fluorine reacts vigorously with this benzene. That is, it forms an explosive reaction. As a result, fluorine cannot react with benzene through electrophilic substitution reaction. Iodine cannot react with this benzene because along with this you get a HX as a product. Hydrogen iodide is formed if you use an iodine here. This hydrogen iodide has to be removed from the reaction mixture because when you use an iodine in this reaction, it is a reversible reaction. Hence, according to Le-Chatelier's principle, you have to remove this one of the product to get your iodobenzene as the product. Hence, this reaction becomes reversible if you use a iodine. Hence, iodobenzene cannot be prepared, or it is not favorable to prepare your iodobenzene through this method. The next method is Sand-Meyer's reaction, very important reaction, named reaction. As I have told you, you have to make a note of all the named reactions in the last page of a note, so that at last you get all the named reactions at one place. So first let us see, how does this benzene diazonium salt comes into existence? That is from aniline. What is the formula of aniline? C6H5NH2. It's an aromatic primary amine. aniline. This you have to react it with NaNO2, sodium nitrite plus HCl. And the temperature of this reaction mixture should be 273 to 278 Kelvin. That is nothing but 0 to 5 degrees Celsius. That is, you have to keep this reaction mixture in a cold bath or a ice bath. Remember, you have to add NaNO2 plus HCl. This reacts to give you HNO2. What is this HNO2? It is nitrous acid. So, nitrous acid is not stable as your nitric acid. Hence, here you are preparing your nitrous acid in situ. I think you know the word. What do you mean by in situ now? You are preparing a reagent inside the reaction mixture itself. That is, you are preparing HNO2 inside the reaction mixture itself by reacting NaNO2 plus HCl. So now aniline is ready. You have added NaNO2, sodium nitrate plus HCl, and the temperature is maintained at 0 to 5 degrees Celsius. You get this benzene diazonium salt. Nitrogen valency is 3, but this nitrogen has 4 valency, hence I have to add a positive charge here. The compensation of positive charge is Cl minus. There is no bond between this nitrogen and this chlorine because nitrogen's valency is 3, it is satisfied completely, hence no charge. But here it has 4 valency, as a result I have put a positive charge. So this is commonly called as BDC. It's a common name, that's a short form BDC. What is BDC? It is benzene diazonium chloride, benzene diazonium salt. Then what you have to do, you have to react it with cuprous chloride, or you can also react it with cuprous bromide. Any salt, cuprous chloride or cuprous bromide, respective haloarenes coming out. So if you take cuprous chloride, you get your chlorobenzene as the product, or if you use your cuprous bromide, you get your bromobenzene as the product. From this Sandmeyer's reaction, either you can prepare chlorobenzene or bromobenzene by reacting with your cuprous salt of either chloride or bromide. Along with this, there will be an elimination of nitrogen. This will be eliminated as nitrogen. There is another reaction wherein iodobenzene can be prepared by this method, by this BDC, that is benzene diazonium chloride, wherein react this benzene diazonium chloride with just potassium iodide, not your copper salts. You do not require any copper salt. Shake this benzene diazonium chloride with potassium iodide. It gives you iodobenzene as the product. It is also one of the method wherein benzene diazonium chloride can be converted into iodobenzene. This benzene diazonium chloride can also be converted into fluorobenzene through reaction with HbF4. That is, reacting your benzene diazonium chloride with HbF4, you get your fluorobenzene as one of the product itself. That is, by reacting with potassium iodide, iodobenzene is obtained. By reacting with fluoro, that is HbF4, you get your fluorobenzene. And this reaction is called as Schiemann reaction, and this is for your CET. So from diazonium salt, you can prepare all type of haloarene. Through Sandmeyer's reaction, you can get your bromobenzene and chlorobenzene. By reacting with potassium iodide, you can get iodobenzene. By reacting with HbF4 through Schiemann reaction, you get your fluorobenzene. So this is the only method wherein you get your all types of haloarenes from your benzene diazonium chloride. Hence benzene diazonium chloride is called a very important synthetic application molecule where you can synthesize a lot many compounds from benzene diazonium chloride. You will be studying in detail about this benzene diazonium chloride synthetic application in your amines chapter also. So the last method of preparation of your halo compounds is your halogen exchange reactions. A very important type of reaction. That is because as you have seen the methods of preparation of your halo compounds here, you rarely prepare your fluoroalkanes and your iodoalkanes from last two methods that we have studied. Either maybe it is from alcohols or it is from hydrocarbons. Rarely you are preparing your fluoro and iodo compounds, iodoalkanes. As a result, this is one of the special method wherein you can prepare your fluoro and iodobenzenes very easily through just a halogen exchange reaction. So as we have known, fluoroalkanes and iodoalkanes are not so easy to prepare either from your alkanes or from your alkenes or even from your alcohols. Hence, this is a special type of reaction wherein you prepare fluoroalkanes and iodoalkanes. So let us see the reaction. The first named reaction, that is the first halogen exchange reaction, is Schwarz reaction. Very important named reaction. I am remembering you then and there that write the note of your named reaction at the last page of your notes so that it will be very helpful at the end of the exam. So Schwarz reaction is synthesis of fluoroalkane. It is the synthesis of fluoroalkanes. So let us see how that is synthesized. It is synthesized from bromoalkane. This is your bromomethane. Upon reacting with silver salt of fluoride, that is silver fluoride, you get this CH3F plus AgBr. So this is your fluoromethane. So this is the method for the preparation of fluoroalkane. So fluoromethane is obtained by reacting with the silver fluoride, silver salt of fluoride. So instead of silver fluoride, you can also use the fluoride salts of either mercury, cobalt or antimony. You can use the salt of these three elements also for this Schwarz reaction, and you can also use a chloroalkane also. So you can observe that there is a simple exchange reaction between these two halogens, fluorine, bromine. I think you can observe this. So hence it is called as halogen exchange reaction. That is, you are exchanging a desired halogen from an existing halogen. So this is your desired halogen to get your fluoromethane. The existing halogen is bromine. So you are replacing or exchanging your fluorine with bromine. As a result, you get your fluoromethane as the product. So it's a very important reaction. So remember these salts, very important for your CET. So they can ask, this is the salt, what is the product? The next halogen exchange reaction that we have to study is Finkel-Stein reaction. So this is the preparation of iodoalkanes. It is the halogen exchange reaction which fetches you your iodoalkanes. So this is the preparation of iodoalkanes. Schwarz reaction is exclusively for the preparation of fluoroalkanes. So take your haloalkane, say bromoalkane, react it with sodium iodide. It's a salt, again it's a salt. So your bromomethane reacting with a salt, that is sodium iodide. So it's a sodium salt of iodide in presence of dry acetone to give you iodomethane as the product. So again it's a simple halogen exchange reaction. The desired halogen is iodide. The halogen exchange to be exchanged is your bromine. So hence there is an exchange to get your iodomethane as the product. So remember this salt, which is a salt used for the Finkel-Stein reaction. It is your sodium salt of iodide, sodium iodide. So this gives you the preparation of iodomethane from your bromomethane, or even you can use your chloromethane for this process to get your iodomethane as the product. So this is about your Finkel-Stein reaction and Schwarz reaction. So with this we have completed the preparation of both haloalkanes as well as haloarenes. So from the next sessions we will be discussing about the physical and chemical properties of your haloalkanes and haloarenes.